graduate student in BioMed, and I'll be your journal club speaker today. So we will talk about this paper in Science Advances entitled Quantifying Interventional Causality by Knockoff Operation. And as usual, let's start by reading the abstract. Is everyone done with reading the abstract? So can anyone tell me what the gap sentence?
First sentence, but I think it's just some general gap.
Yeah, I agree. So in the first sentence, it says it gives us a general problem with the whole field of causal inference. So it's saying that it's very important, but it remains challenging. But that is a very broad gap. And since it's introducing a new method for causal inference, then for a very specific gap, it should identify what is the problem with the previous approaches. Then that should be a strong gap. Do we have any other opinion about this abstract or questions? No? Okay, so first, let's start by introducing just the concept of causality, because I think not everyone is familiar with the concept of causality. So basically, conceptually, causality is just a directed relationship between two variables where changing one variable results in the changes in another variable. So a very simple example here is physical activity and your heart rate. So we know, obviously, that when you increase your physical activity, then it results to a higher heart rate. And because we know that if we plot your activity intensity versus your heart rate, we expect this kind of relationship, right? So we increase our activity intensity, our heart rate also increases. And we know this relationship is causal because it's supported by physiological knowledge. However, not all variables that result in this graph imply causality. Okay, so this one we know that it's true because it's very obvious. However, sometimes we can see some other type of graph that results in the same behavior, but if we check the variables being compared, they are not really causal. So x-axis is ice cream sales and y-axis is the number of sunburns. But we know, obviously, that increasing the ice cream sales will not result in increasing the number of sunburns, right? Because obviously, these two is like mediated by another external variable, for example, higher temperature or the intensity of the sun, right? So obviously, these two variables are not causal. So then, if if these two graphs are very similar, our question is how can we detect causality and distinguish it from correlation? And one very reliable way of determining causality is by performing experiments or interventions. So this is where interventional causality comes in. So it allows us to ask the question, what happens to a variable y if we change something in x? So in the example for physical activity and heart rate, we observe that increased activity is also increasing the heart rate. And the experiment we can do here is that we can slow down the physical activity, and we will see that your heart rate will also decrease. So in this case, we can say that there is some causality. However, in the second example, for ice cream sales and sunburns, we can stop selling ice cream, but then since the temperature is still high, stopping the selling of ice cream will not decrease the number of sunburns. So in this case, there is no causality. However, in many real systems, we cannot always do some experiments. So direct interventions are not feasible or impossible. So for instance, we observe that whenever it's raining, the mood of one person is very happy. However, we cannot force the weather to be sunny, so that we don't know what will happen to the mood of that person, because we cannot do this experiment. So this is where the method in the paper comes in. It is called the knockoff conditional mutual information, or COCMI. It detects interventional causality without having to do any physical interventions or experiments. But to know about the method they presented, we need to know two things. First, we need to know what a knockoff is, and we need to know what conditional mutual information is. And furthermore, to know about conditional mutual information, we need to know what mutual information is. So I will first introduce the concept of mutual information. So first of all, conceptually, mutual information quantifies how much information is being shared between two variables. And we can easily see it in the formula for the mutual information. In particular, that fraction, because as you know in basic statistics, if x and y are independent, meaning there is no shared information between two variables x and y, then the joint probability of x and y is just equal to the product of the probabilities of x and y, right? So then what happens to this fraction inside? It will just be equal to 1, and the mutual information will result to 0, meaning there's no shared information between the two variables. So we illustrate this by a very simple example. Here we have the variable x, which is knowing whether it rains, and the variable y, meaning bringing an umbrella. So we have 100 observations, and we have the corresponding counts for each combination of events. So since we know the count of each specific event, we can make this type of table, right? So we can see here the probability of x and y being both equal to 0, that's just 0.4, and x equal to 1 and y equal to 0.1. So basically, we just plug it into the formula for the mutual information. That means we have to solve this quantity for each combinations of values of x and y. So when x equals 0 and y equals 0, we have this term. So the joint probability of X and Y is just 0.4. You can see that in the table. And the probability of X, you can see that it's just X being 0, that's just 0.5, and Y being 0, that is also 0.5. And we do this for each combination of X and Y values so that if you compute it, you will have a value of 0.278. And the way we interpret this is like this. So when knowing whether it rains will reduce the uncertainty of bringing an umbrella by 0.278. Now, let's take a look at another example. Here, we replace the variable X by knowing if it is weakened. And again, we can construct this table where we write the probabilities of each combined event of values of X and Y. So, I made it very simple. So each combination has just a joint probability of 0.25, and that means that each term will just have 0.5, right? And you can see that this quantity will just be 0.25 over 0.5. That's 1. So that even if we multiply it by 4, the mutual information is just equal to 0. So that this means that even if we know that it's weakened or not, it doesn't give us any information about bringing an umbrella. Okay? Yeah, so mutual information also can be interpreted by how much knowing one variable can reduce the uncertainty about another variable.
Left side, do we interpret other way, like knowing whether we use the umbrella, reduce the uncertainty of the region by 0.2?
So in this case, since I put specific variables, I think the other way around doesn't make much sense.
I know, but from just this week,
Yes, from just this data, it's just supposed to be
that concept, I think, need the entropy. Whether here, well, what about this? So, if you calculate the future information, can we interpret this way? Whether we bring reduce uncertainty, we're bringing 7. This is also not the transplant. There are two X, Y, on so MI X, Y minus certainty of the one. Yeah, you're right. So ensure information amplifies how much uncertainty reduced by knowing. So that reverse way is fine. So here, although she wrote in this way, we don't know the causality. So either way, knowing the people using the umbrella can reduce the uncertainty of the rating by 0.6. Anyway, it's richer for that to reverse. So
that's still the mature information is kind of correlation. Correlation is still not.
So at this point, yeah, that is correct. So mutual information is still some kind of correlation. But now we will look at an extension, some sort of extension of the mutual information. So we will talk about conditional mutual information. So it quantifies how much information of two variables share, given that we know another variable. So again, the formula is very similar to the one for the mutual information. The only difference now is that we know another variable z. So the probabilities in this fraction is just conditioned on z. So we can take the same example as before. We have rain, umbrella, and another third variable, which is the forecast for rain, whether there is a forecast of rain or not. Yeah, so same as before, we just follow the formula. And since we only have 4 rows of non-zero joint probabilities, we can write it in this way. So again, I made it very easy. All the probabilities are just equal to each other. And if we compute this quantity, it's just equal to 1. So this way we can say that given the rain forecast, so that is the condition variable, knowing whether it is raining will give full information about bringing an umbrella. So that is just the difference between the mutual information and the conditional mutual information. Okay. But again, we have another question. How do we know that the computed value for conditional mutual information is meaningful? So far, our examples are all binary variables, but if the problem becomes more complicated, we don't know how to interpret the value here. So actually, the conditional mutual information is always non-zero, but being non-zero will not always tell us that there is a meaningful information. So how do we know that it is meaningful? One common way for assessing the significance of the conditional mutual information is by comparing it with surrogate data. So what is surrogate data? Conceptually, it gives us a scenario where there is no influence between the variables. Okay? So I will give you a very simple example and one very simple way of producing surrogate data. And that is through permutation or just random shuffling. This is the most common way of producing surrogate data. So for instance, we have 3 variables, x, y, and z. And I only plotted here the variables x against y. And you can see that there is like an increasing correlation between them. And let's say that the computed CMI is equal to 0.9. Now, what we do is just shuffle x many times. So in this case, we are shuffling what we think of as the causal variable. We shuffle it many times, but we keep the order of the variable y. So if we do that, we will have something like this. Okay, so we plot the shuffled x against y, and we do it again and again, and we do it many times. So let's say we shuffle it 300 times. Then, since we shuffled the x variable 300 times, we can also we can see here in the plots that the dependence between x and y is completely destroyed, right? We cannot see an increasing correlation between them. And since we shuffled our x values 300 times, we can also compute the resulting conditional mutual information 300 times, right? So we have 300 values of CMI, and using that 300 values, we can create some distribution of that value, right? So here, the gray bars correspond to the conditional mutual information from the shuffled data. And what we do is we compare the score from the unshuffled data. That is the 0.9. Okay. So we can see here that the computed value from the unshuffled one, or the original value, is very far from this distribution. And what does this distribution represent? This is the kind of the null distribution, or this is what we expect if there is nothing going on between x and y, right? And if the CMI from the original value is very far from this distribution, then do you think that this is by chance? This score is just by chance? No, right? Because it's very different from this distribution. So that is one way to assess the significance of your computed CMI. However, there's a problem with just random permutation. So the first issue is that, remember, we are computing the conditional mutual information. So if there is some relationship between x and y, it is also destroyed. That's one issue. And second issue is that the surrogate data that we produce from just shuffling, it's too easy to distinguish from the original one. So you can see here in the plots for the x shuffled versus the y. It's just very scattered data. There's no structure. And of course, if we compare it to the one in the original plot versus x versus y, it's very different from the increasing correlation. So the question now is, can we design a better surrogate data? This is where we introduce the idea of knockoffs. So I'm going to show you what.
I think this is gap sentence of this study.
Yes.
So if you are confused, you should ask the question now. If you don't understand this gap, follow-up thing will be according to weeks.
How do you choose the variable that we wanna do computation? It has some
Okay.
specific meaning, or is it just metric? It's some kind of choosing variable.
You mean how do we know that we will shuffle x?
Yeah, or also is the results the same if we change x or if we change y?
So in this case, usually what we do is we shuffle our suspected causal variable. So if we think that x causes y, and so we test what happens if we just shuffle y.
Do we assume that x causes y?
We don't assume it, but we suspect that x might be causing y, and that is what we will test.
And that's why we take this.
And if we also suspect that maybe y also causes x, we can also do the same thing. Just shuffle y, but maintain the order of x.
Let's think about it. If we want to know whether x caused the y, then why do we shuffle the x, not the y? Let's think about it. I think this is key point. If we want to test X cause Y, why do we shuffle? Why we mess up the X? What's the difference? Messing up the X or messing up the. This is a key point. If we know, like a temperature affect the ice cube cell, if we want to test that, why we shuffle the temperature data, not the ice cube cells? 하지 않아요? X를 셔플하나 Y를 셔플하나 그걸 모르겠어. 왜 close만 셔플할까요? X를 셔플해도 messup이 되고 Y를 셔플해도 messup이 되고. Why we only mess up the X? We need to explain that. Any idea? The key is we want to know the null distribution. Why messing up the X can generate the null distribution or the causality from the X to the. I also don't know the answer. Please think about it. 이거에 대해서 너무 얘기.
Y를 셔플 한다고 해도 그러니까 널 디스트리뷰션을 얻는다는 건 X가 Y를 커즈하지 않는다는 가정을 한다는 건데 Y를 셔플해도 X가 Y를 커즈하지 커즈하더라도 Y를 셔플하면은 사실 X는 안 바뀌는 거니까 그러니까 사실 커들리티를
그럼 한번 이렇게 해볼까? 그 간단한 질문. Let's do the simple question. If we shuffle the X or shuffle the Y, let's calculate the mutual information. So let's calculate the mutual information of the shuffled X and fixed Y, and mutual information of shuffled Y and fixed X. Are they different or same? Let's begin that part. Mutual information X, Y가 X를 흔드는 거랑 Y를 흔드는 거랑 계산 결과가 바뀔까 안 바뀔까?
네네.
여기서부터 출발할까? 같으면 이거 뭐 할 필요 없는 거지? 다른가? 왜 다른가?
컨디셔널 그거 없으면 같은.
그러니까 컨디션 없다고 생각을 없으면 같은. 그치? If we don't have a condition, if you shuffle the X, shuffle the Y, my expectation is my X and Y are the same. Yeah, if we actually, I also not sure under condition of the G, but if just we use the mutual information X and Y, it's very symmetric. Perturb the X or perturb Y to me, same null distribution.
It's information is correlation.
Yeah, because it's correlation. So that means maybe If we shuffle the both n, x, y might be same. That's my expectation. Right. Okay. Then even z, I don't know. Anyone can ask the ChatGPT or Gemini under conditioner the mutual information x and y can be different if we shuffle the x and y. Anyone? In front?
CMI 식 보면은 PXYZ 텀이 있는데 나머지 부분 사실 이 부분은 다 똑같은데
그치.
PXYZ 텀을 생각을 해볼 때 X를 셔플하면은 PX 곱하기 PYZ가 될 것이고 Y를 셔플하면은 PXZ 곱하기 PY가 될 것이기 때문에
다를 수도 있구나. Okay, good point. In the conditional term, we have this three variable joint distribution. 이게 달라질 수도 있겠구나. 그럴 수도. 오. 그런가 보자. 이 친구의 표현은 if we shuffle the x, this will be similar to. But if we shuffle the x, that means x become independent. So that this probably will be approximate by the px time. Actually, not approximate, equal. If we shuffle the y, so condition correlation between xg is only left over. Here only condition is y and g are left over, so they could be different. Whoa. Good eye. Wow. So that means at least for given z condition, mutual informations are different. If we shuffle the x or if we shuffle the y, that's good. And very good point. So if we shuffle the x, only this part is left over. Correlation between y and z are sort of the left over because it's condition z. 다르구나. z가 집어넣었을 때. Okay, then at least we know that they are different. Then let's go back to our original question. Why we shuffle the x to know the causality is x to know y. Why we mess up the x? So the null distribution is only x is gone. Only the relationship y and z are sort of the leftover. 재밌네. 물리학 전공 있으니까 좋구만. 이거 하는 거지, 너희 분야는? 이런 거.
네, 합니다.
훌륭하다. 수학하는 사람들 힘내시고. 이걸 설명할 수 있어, 우리 좋은데. 왜 우린 X만 흔들까? X가 독립이 돼버리고.
독립이면 사실 값이 0이 나오고
아니, X만 빠지고 YZ는 나옵니다.
Y도 어차피 왜 분자에 뭐 있는 거
그래서 다 돼버려, 0되구나. 그런가? 그런 친구가. 그럴 수도 있겠구나. 그러네.
데이터면 아예 0은 아니더라도 차이는 있는 계산값의 차이는 있는
그런데 거의 0이다. 여기서
보면
이 널 디스트리뷰션이 좀 남는 이유가 뭘까? 우연. 그러니까
사실
우연이라도 이렇게 높이 될 수도 있는 거잖아. 우연이니까.
사실 저거는 데이터 개수가 충분하지 않아요. 바이어스가
바이어스가 생기게 돼서 그게 널 디스트리뷰션이죠. 그럼 얘 원래 그 오리지널 값은 0이 돼야 되는 게
여기 막아도
데이터가 충분한 거.
예.
음수도 될 수 있는 거야. 아니지.
풍선은 어때? 저게 문법에 저렇게 그려놨고 원래 실제 문법은 저게 아닐 수도 있고
이렇게 돼야 돼.
아마 그런
아마 is it from the paper?
No, sorry, it's just for illustration.
It's illustration. So I guess this. Okay. So far, if we summarize it, if we shuffle the x, then x become independent from the y and z variable. Then the mutual information will be 0. So that mean will be the 0. But data is not large enough so that it can be non-zero due to the randomness. So we may have this kind of tail. And then hopefully this blue point is in the very tail that we can say that what we observe is not just a random event. Okay. 그럼 여기서 이제 질문은 X를 셔플해도 Y를 셔플해도 다 0이 픽인 이런 테일 형태일 텐데 이게 과연 다를까? G가 주어졌을 때. 그러니까 우연히 퍼즐이 그게 갈리는 거고 일단 네, 넘어갑시다.
So as I mentioned earlier, there are some issues with just random shuffling, and we want a better surrogate data. So this is where we introduce the idea of knockoff surrogates, and I will give you an idea based on just an example where we have just 3 variables, x, y, and z, and we want to test if x has any effect on y. So there are 2 conditions for a knockoff x tilde for x. The first condition is that x tilde has the same relationship with other observed variables except the outcome variable. So in this case, what is the outcome variable? It is, since we want to test x, the effect from x to y, then the outcome variable is y. Okay, but the first condition asks us for the same relationship between the knockoff x tilde and the other observed variables. So in mathematical terms, so the joint distribution of x and z should be the same with the joint distribution of x tilde and z. Okay, so if we replace x by the knockoff, then the distribution should still be the same. So we can easily demonstrate it in this way. So we plot here x versus z. So those are the original variables. And we also plot x tilde, that is the knockoff, versus z. So you can see here that the behavior is preserved, although x and x tilde are not equal. Okay, that is the first condition. And the second condition is that if we replace x by its knockoff x tilde, it should not change the distribution of the outcome variable y, unless x is causal. So in other terms, this means that the probability of y given x and z should be equal to the probability of y given the knockoff x tilde, and this is the case where x is not causal. So that means if we replace x by a fake version of it, then there should be no changes in the distribution. But so somehow it looks like this. 2 distributions are the same. However, if replacing x by the x version will destroy that distribution, then we can say that x is causal to y.
This is called condition or not? What do you mean why you call this?
So this
If x is not causal, we need left side, and if x is causal, we need the right side. That's the condition.
yes.
Okay, so depending on exposing the y or not, okay, you need left side or right side as a condition. So we need a surrogate test. We need a new surrogate method for the x. The new surrogate method should satisfy a left side condition. So condition variable and x variable have the same joint distribution. And another condition is, here is two cases, x is actual close and x is not actual close. And depending on, we need this, okay? Okay.
So these are the conditions that the knockoff or the fake version of X should satisfy. So this is why in the abstract they called the knockoff as a virtual intervention. So we are replacing X by a fake version of itself, but we are still preserving some data structure, as you can see from condition 1. So now the question is, how can we construct a knockoff? So we have the same problem here. We have x, y, and z variables, and we want to test the causality from x to y. First of all, the outcome variable will not be used in the knockoff generation. Okay. And I will illustrate how to create the knockoff using an example. So I use a simple example here where x and z are joint normal. So first, we are just going to look at the variables that are not the target. And we assume that it is joint normal. And suppose we compute their covariance. And this is the covariance estimated. That is the first step. And the second step is that we introduce a diagonal matrix where the entries in the diagonal will represent how different the original variables are with their knockoff. Okay, so something like this. So we introduce this diagonal matrix where the diagonal entries, let's say 0.8, will represent how different the original variable is from its knockoff. And there is a reason for that, because for the step 3, we will define the joint distribution for the original variable and its knockoff. And one goal is to maintain the original covariance between x and z and the covariance of x till the end, z till the end. So these are the knockoff versions.
Knockoff?
Knockoff, because I think, when we say knockoff bag, like fake Louis Vuitton bag, so they look the same, but one is fake.
We call the knockoff means like a fake.
Yes, but somehow they have similarities. So we want to maintain the covariances between this one, right? So this is to satisfy that in the diagonal entries, we just use the original covariance matrices. And the second condition is that we want to make the knockoff as different as possible from the original one. And to satisfy that, the off-diagonal matrices should be sigma minus 3. Okay, remember that in B, the diagonal entries represent the difference between the original and the knockoff. So that if we subtract it from the original covariance, we will get something like this.
Oh, yeah. So here, Z tilde or G for the omega tilde? We change the G as well.
Yes.
Oh, really?
Actually, in the process, they also make a knockoff for Z.
Yeah, well.
Yes, but if we are just testing X to Y, we don't really use the Z knockoff. We only use it, for example, if we want to test Z to Y.
If we maintain the covariance between x tilde and tilde, can we still say that x tilde has a same distribution with the z? That's why I'm a little bit confused.
Not very sure, but I think the point of this construction is that if we make knockoff versions of x and z, then the resulting covariances should be the same as the original x and z. And if we construct it in this way, we can check the conditions that I showed earlier. So this entry is the covariance between x and z. And if we check the covariance between the knockoff and z, they are equal. And you can check the other entries between the non-equal variables, and this condition is satisfied. So if we replace x by x tilde, it's still the same. And at the same time, the covariance of x with its knockoff is minimized because we want to make x different from its knockoff version. Yeah, so finally, since we have the covariance between W and its knockoff, what we do is we can now generate the knockoff by sampling from the conditional distribution W tilde given W. So the knockoff given that we know what the original variables look like. So given that we know the joint distribution of W and W tilde, we can compute for the conditional distribution. There's a long derivation of this, but if you want to check, I put it in the appendix. So this is just the formula that you have to follow. Finally, since everything in the conditions for the knockoff is satisfied, we can check what the knockoff variables look like. So first of all, I am showing here the original x versus z. And this is the original, the left-hand side. And the three next illustrations are the plots of z versus a knockoff. So you can see that the plot of z versus x, the original variables, are very similar to the plot of z versus a knockoff. So kind of the relationship between z and x are preserved.
Here, knockoff 1, 2, 3, just change of the matrix D.
Yes.
Then the finding x tilde means that finding new x is
Yes.
for x tilde while maintaining the various.
Yes. So that is why the behavior is still the same in the knockoff. And now I also plot the x versus y. So that is the original x versus y. And the resulting x tilde versus y are the colored one. So you can see here that the original one has an increasing correlation. And somehow also the knockoffs are increasing, although some of the structure is a bit destroyed. So it is more scattered compared to the original X versus Y. So now I think compared to the permutation version, now it is more difficult to determine if this relationship is actually causal or not. So now, because this is what we see from the data, if the knockoffs behave like the original variable, then how can we still detect causality? So this is where we combine the knockoffs and the conditional mutual information. So basically, we will compute this difference. The conditional mutual information computed from the knockoff X and Y given Z minus the conditional mutual information from the original variables.
들으면서 오늘 지금 하는 거 생각하면서 Z가 시즈널리티, X의 수, Y, 질병 뭐 해서 좀 이따 해봅시다.
Yeah, so intuitively, if there is no causality, this should just be the same, right? And if you wanna do it, so this is from the knockoff, this is the original variables. And if you just use the formula for the CMI and do some algebra, you can get this formula. But at this point, we recall the condition 2 for knockoffs. Okay, if this equality is true, right, y given x and z is equal to the probability of y given the knockoff is z, then x is not causal. But if this is not equal, then x is causal. So you can see here, if these two are equal, then there is no, then we expect this value to be 0. So there are two cases here. This is 0 when x has no effect on y. And then this is not equal to 0 if x has a direct causal effect on y. So that is the idea for the method in the paper. And then actually we just repeat the same idea of the null distribution as before. So this is the full framework of Cockney. So we have the original variables x, y, and z. We generate the knockoff for x. So here we have x tilde, y, and z. And then we generate many knockoffs. Okay, we compute the conditional mutual information for the original variables, and then we also compute the corresponding CMI here. So we have m values for CMI, right? Then we do the same thing as before. We compute the differences between the two CMIs. So there are m values of that. And we do the hypothesis testing. So the null hypothesis is that this difference is 0. So there's no causal variable. And the alternative hypothesis is that it's not equal to this. So again, we do some hypothesis testing. And this is the resulting distribution of the, if this is the resulting null distribution, if, for example, this one, the original, the computed one from here is very different from this null distribution, then we can say that there is causality from x to y. But if it is very similar to this distribution, then the difference is 0, and we can say that there is non-causality between x and y. So actually, we just do the same thing as before, the producing of the null distribution and comparing the original score. But this time we use a different surrogate data, which is the null.
Question is, larger value of this larger value is better than lower value. So I mean, the value closer to zero is represent there's no other. What's the meaning of positive?
Ah. Okay. So if it's here, I think it should. What we're testing is how different this difference is from zero. So if it's very far from zero, then we have causality, and I think it should be the same here because it's still very different from zero.
If the value is positive, that means the knockoff variable is more. But I'm a little bit confused at that part. So I thought that the original variable, if there is a causality,
Mhm.
then I think that the original variable should give more information. Why? But at this point, the knockoff variable is giving more information.
Yeah, because this is the order, right?
Right.
What's your question?
So CMI, MI, the interpretation is how many information they're sharing.
Share, yes.
Yeah. But knockoff variable shares more information than original variable.
That opens.
And so that definition of dx to y, if that value is positive, then knockoff variable shares more information with y than the leading.
We should be opposite, I guess. Is it true?
Yeah, it's what they wrote in the paper, but I guess it should be flipped.
Yeah, it should be opposite.
Yes.
Not only the figure, what about the paper?
Yeah, it's flipped. It should be.
We look at this formula, it's true or opposite to check it. Because of the calculation. The first one. Yeah, everyone try to calculation. That's correct or opposite? You think, is it correct or wrong?
I think it's wrong because if it's causal,
Oh.
then
I know, in terms of meaning, but.
Yeah.
Is this equal or opposite of equal to?
these are equal, but if
Oh.
we switch this one, this will just switch the numerator and denominator, and this will still be true.
아, 이 저걸 실수한 너무 이해할 수 없는데? 이 논문의 하이라이트인데? Oh, I'm not sure. Can they really make the data for that part? This is a highlight of this paper. Using knockoff minus user. When they published,
Just this October.
well, but it has been 3 months, so there is no error term. This is too serious error. The error term is not only.
스코어를 받을 때 절대값을
어?
스코어를 받을 때 절대값을 쓰는 거. 근데 제가 모르겠어. 이게 뭔가 좀 혼란스러운데 왜 저렇게 되는 거야?
절대값을 쓴다고? 앱소드 빼기?
오 마이 갓. 내가 무슨
음수가 나오면 어떡하려고? 좀 이상한데, 이거. 왜 이러시지?
이게
심각한데? 오, 설마, 뭐 이렇게 하지? 이게 실수였나? 아닌 것 같아. 뭐, 말이 안 되는데? everyone 논문 한번 읽어볼래요? 메소드나 이런데. 이번 팀이면 이거 실수했었는 아닌데. 이런 씨. 이건 컨셉이 같습니다.
아무거나 별 있다고 생각을 해야 될 것 같은데 계속 진짜 어려워.
하는데 혹시 나와 있지? What's in English? Which look? Explanation. 그렇게 하고
This is not a mistake.
거의 부호랑은 상관없는 것 같아. 뭐 그냥 릴레이션 하는 거. 이거는 그냥 특수한
음수일 때가 많은 것 같은데? 그리고 그래서 그냥 절대값을 씌워서 하는 거 같아.
네.
그치.
무수가 나오죠.
정상인 거 같아. 맞아요. 네. 지금 뭐, 바꿔서 써도 똑같은데, 왜, 자세히 이거를 모르겠네. 저거가 철학이 있는 것 같은데. 이거는 수학자들이 왜 저러지? 보통은 펄펄부 한걸 뺄 텐데. 그다음 그걸 EXY라고. 조금 version이 있다. 두, 이거 두 calculation은 이렇게 하는 건가? 그렇진 않죠.
또는 그 스트럭처럴 모델을 만들고 나서 있는 거가 단순한 데피니션일 텐데 이거랑 관련이 있다고 그러니까 컨시스턴트하다고 나와요.
이런 식으로 정의하는 게.
예. 근데 각 자체에 대한 의미에 대해서 컨시스턴트하다고 한 것 같은데.
그러니까, 오. Okay, so I think Older didn't make a typo. I think this is their real definition, but they only consider either zero or non-zero. So actually, negative means causality, but they use the absolute value of this anyway for the X-ray. But they may have some reason why they use this on conventional notation, but I don't know. Okay, so let's move on.
So actually, this is the full framework, and I'm just gonna show the applications. So we will see how the method performs in usual network motifs. So they tested this method in well-known network reconstruction against other well-known network reconstruction methods. So these are the usual network motifs where causal inference methods are tested. And the reason is that there is a usual wrong result for these types of networks. So for example, for the first one, there are two ways where Z can affect Y, right? So Z directly affecting Y, or it can affect Y through X. But the common result is that only the direct result is being detected. And for the fan out, since there is a third variable affecting both X and Y, a usual wrong result is that X affects Y directly. And it's the same thing for the sequential one. Even if there is a third variable, like a mediator variable affecting X to Y, the usual wrong result is that X affects Y directly. It's the same thing with the fan-in. Since both X and Y affect Z, a wrong usual result is that X affects Y. And finally, if we have a loop, you can see that there are many indirect causalities that we can see here. So for example, X affects Y through Z, but the wrong detected network is that X affects Y directly. So these are the common, this is why these are the usual networks where causality is being tested. But when we compare their approach against other causality methods, we can see that for both the AUROC and AUPRC, it is outperforming all the usual methods. And one more way they tested the COPMI is through the Dream Network Challenge. So what the Dream Network Challenge does is that they give information about several variables. So for example, they give data on gene regulatory networks. For example, we have 10 genes and we have all the gene expression data. And then the goal of this Dream Network Inference Challenge is to draw the arrows between them. So this is an annual thing, and they don't release the answer until after the challenge is finished. So, but I think this paper used the previous year's data so that when they compare it to other network inference methods, this is the result. So these are spiderweb plots for AUROC and AUPRC. Middle value is 0, and the outer values are higher. So you can see that the COPMI one is the red line plot and then red dot here. And for the 5 networks where they tested this method, it is almost always superior than all the other methods. And if you get the mean value for the AURC and AUPRC, it's always it always gives the higher values compared to the others. So actually, they tested it on other data, but generally the conclusion is that it's more superior than all these other network inference methods. So that's it. And before I finish the presentation, I have 3 take-home messages. So first, the knockoffs will enable virtual interventions from observational data. It can give you fake data that behaves similarly to the original one. And second, their method in this paper combines the conditional mutual information and knockoffs to detect interventional causality. And finally, one important thing is the significance of some inferred causality is assessed via comparison with a null distribution. And that's